Today, we'll learn about PN junctions, which are fundamental to understanding how semiconductor devices like diodes and transistors work. Let's explore this important concept together. Before we dive into PN junctions, let's briefly understand what semiconductors are. Semiconductors are materials that have electrical conductivity between conductors like metals and insulators like glass. The most common semiconductor material is silicon. Pure semiconductors aren't very useful on their own. To make them useful, we add impurities in a process called doping. This creates two types of semiconductors: N-type, which has extra electrons, and P-type, which has holes or missing electrons. Now, let's see what happens when we join a P-type and an N-type semiconductor together. This creates what we call a PN junction, which is the basic building block of many electronic devices. On the left, we have the P-type semiconductor with positive holes. On the right, we have the N-type semiconductor with extra electrons. When these two types of semiconductors are joined together, something interesting happens at their boundary. Due to the concentration gradient, electrons from the N side start diffusing toward the P side. Similarly, holes from the P side diffuse toward the N side. When electrons and holes meet at the junction, they recombine and neutralize each other. This recombination creates a region around the junction where there are no mobile charge carriers. This region is called the depletion layer or depletion region. Notice that the depletion layer forms right at the junction between the P and N regions. This is very important to understand. The depletion layer is not the entire semiconductor, but just a small region at the boundary. As electrons and holes recombine at the junction, they leave behind immobile charged ions. On the N side, we get positively charged donor ions. On the P side, we get negatively charged acceptor ions. These immobile ions create an electric field across the depletion layer, pointing from the N region to the P region. This electric field creates a potential barrier that prevents further diffusion of majority carriers across the junction. Eventually, the system reaches equilibrium, where the diffusion force is balanced by the electric field. Now let's see what happens when we apply external voltage to this PN junction. When we connect the positive terminal of a battery to the P side and the negative terminal to the N side, we call this forward biasing. This external voltage reduces the potential barrier at the junction. As the barrier is lowered, more majority carriers can cross the junction, resulting in a large current flow through the diode. This is why diodes allow current to flow easily in the forward direction. Conversely, when we connect the negative terminal to the P side and the positive terminal to the N side, we call this reverse biasing. This increases the potential barrier height. With a higher barrier, almost no majority carriers can cross the junction, effectively blocking current flow in this direction. Only a very small current, called the reverse saturation current, can flow due to minority carriers. The PN junction is the fundamental building block of many electronic devices. Diodes are simple PN junctions that allow current to flow in only one direction. Light-emitting diodes, LEDs, are PN junctions that emit light when forward biased. Solar cells work in reverse, converting light energy into electrical energy using PN junctions. Transistors, which are the basis of all modern electronics, use multiple PN junctions to amplify signals. To sum up, a PN junction is formed when P-type and N-type semiconductors are joined together. Key points to remember: the depletion layer forms at the junction and contains almost no mobile charge carriers. A potential barrier develops at the junction due to immobile charged ions. Forward biasing reduces the barrier and allows current to flow. Reverse biasing increases the barrier and blocks current flow. These principles are fundamental to understanding how semiconductor devices work in our everyday electronics. Thanks for watching.